Okay, great. So today, for our first colloquium of this the spring quarter, we're happy to have Azadeh Maleknejad visiting us from CERN, and she will talk about the universe as a remnant of the Chiral anomaly during inflation. Please uh, take it up from here.
Thanks, Victor. Good afternoon, everyone. It's a real pleasure and, in fact, an honor for me to speak at SITP. And the reason is that, as you see, the topic of my talk is related to cosmic inflation. So cosmic inflation is now part of the standard paradigm of cosmology, and it's based on pioneering works by one of the giants of modern cosmology, Professor Linde, who is at SITP. So, and actually, he with his collaborators studied several aspects of cosmic inflation, but he was kind to leave something for junior people like me to explore, and that's gauge fields in inflation. Today, I'm going to tell you about embedding axion-inflation in gauge extensions of the standard model and its predictions for cosmology. I hope by the end of this talk, I can share some of my excitements with you. Okay, let us start with a brief recap of what we already know about the cosmic history. We know that our universe started too tiny, too hot, and probably from a big bang, and is expanding ever since. For many years, it was filled with a hot plasma, and it was totally opaque because photons keep bumping into other particles. But the universe gets colder and colder as it expands, and eventually it got cold enough, like the temperature gets around 1 electron volt, so the neutral atoms could form. And at that point, photons eventually got free to stream through this plasma, and for the first time, like cosmic microwave background, or CMB, is formed. Which is basically the first snapshot of the universe, and technically the first selfie of history, because that's the selfie of the universe from itself when it was super young. And then the universe kept expanding, getting colder and colder. Eventually, this hot neutral atoms got cold enough to assemble and gravitationally collapse to form the large-scale structures that we see today. Too simple yet profound. In fact, our universe turns out to be too simple, too symmetric at very large scales. And CMB is nearly homogeneous and isotropic all over the sky, with teeny tiny fluctuations of order 10⁻⁵. The leading paradigm to explain that unexpected symmetry in very large scales is the cosmic inflation pioneered by Professor Linde and Professor Guth. And that's basically a period of exponential expansion of space shortly after the Big Bang, during which the size of the universe, the radius of the universe increases by a factor of e to 16. Just to have a rough idea about the size of this number, that's basically the same as if a bacterium suddenly starts growing, and in a fraction of a second later, it becomes as big as the whole Milky Way. So it's a huge number. But what caused inflation? The exact particle physics of inflation is still unknown, but a scalar field slowly rolling towards its true vacuum provides a simple model for inflation. And the idea is that we assume that the universe is filled with this homogeneous scalar field, let's say this scalar singlet beyond the standard model. And in case that it has a flat potential, and the kinetic term of this field is much, much smaller than its potential, what is happening is that then basically we would have something like a quasi-expansion, a quasi-density expansion for the universe, which provides a slow roll inflation. So far, so good, yet things get way more fun when we turn on quantum fluctuations. Due to uncertainty principle, quantum vacuum is not nothing or empty, but it's this vast ocean made of virtual particles which are getting generated and annihilated in a fraction of a second later. But on the average, still we have nothing. However, in the presence of a background field, if it's strong enough, it can upgrade these virtual particles into actual particles. And some examples of such background fields are an electric field that can generate particles by the Schwinger effect, or gravitational field, which can produce particles gravitationally. In fact, the inflation itself can produce particles. So here we have the flat space case. We start from vacuum, and then at a fraction of a second later, we have this virtual pair of particles, but then shortly after that, they find each other and annihilate, and we end up with vacuum. However, in an expanding universe, if it's expanding very, very fastly, what is happening is that imagine we have this virtual pair of particles that they want to find each other to get annihilated. But by the time they want to find each other, the space underlying them expands so fastly and vastly, they cannot find each other. And as a result, it produces particles. This effect first has been discovered by Schwinger right at the beginning of World War II. But he was so shocked by his discovery that he called it an alarming phenomenon. 80 years later, now we have a very different point of view about this effect. In fact, we know that exponential expansion turns these initial quantum vacuum fluctuations into actual cosmic perturbations. So imagine this world in which, for example, there were no fluctuations in inflation, then we will have like an exactly homogeneous and isotropic CMB and no large-scale structures. However, these tiny fluctuations, quantum fluctuations that get upgraded to cosmic perturbations by inflation, eventually get imprinted on CMB and forms this CMB anisotropic, and eventually they get to the large-scale structures that we observe today. So we are the product of quantum fluctuations in the very early universe. It's part of that initial quantum fluctuations had the structure of a scalar, so they form density, like density fluctuations. Another part of that has a nature of a spin too, so they are basically gravitational waves. And these primordial gravitational waves are tiny waves in the fabrics of the space-time that squeeze and stretch anything in their path as they pass by. Their field equation is super simple. They're basically given by box Hij equals 0, and this Hij is basically just a spin-2 field. It has 2 dynamical degree of freedom, so I can decompose it in terms of its 2 polarization states, H minus, the left-handed polarization, and H plus, the right-handed polarization, because these are just vacuum gravitational waves and sourceless. They are unpolarized. And since they are just given by the Ricci scalar, they are nearly Gaussian. And also they contribute to CMB polarizations. Interestingly, these primordial gravitational waves are very powerful, and their power is in their weakness. The reason is that, so CMB photons, they are easy to detect, yet they are easier to block. And that's why they can only tell us up to the surface of last scattering or at the surface of CMB. Gravitational waves, on the other hand, they are hard to detect, yet hard to block as well. So if they get detected, they can tell us about all the way back to the very early universe and the physics of inflation. So that makes them extremely valuable, and that's the reason that several missions are there to observe them, including two CMB missions, Lightbird Satellite and CMBS-4. Fingers crossed for them. As yet, we know that observations are in perfect agreement with the concept of inflation. However, the particle physics of inflation is still unknown. And the standard models of inflation are mainly based on scalars, meaning that we are extending the standard model of particle physics with this scalar singlet that we called inflaton. And its connection with the standard model is not clear yet. And in case that this is all the physics of inflation, that gravitational waves are sourceless, therefore they would be unpolarized and Gaussian. Okay, but what about gauge fields? What do they do in inflation? Before getting to that question, let us have a brief summary of the current puzzles of the standard model and cosmology. One of them is, of course, the particle physics of inflation, that how to embed the inflaton to the standard model or any model of particle physics, the origin of the matter asymmetry, the origin of the neutrino mass, and the particle nature of dark matter. I think the origin of neutrino mass is sort of a famous problem, and that's basically this fact that in the standard model, we have only left-handed neutrinos and they are massless. And we know that most of our universe, like a large fraction of matter in the universe, is not baryonic and is something most probably beyond the standard model. The issue of matter asymmetry might be a little bit just for let me just give you a brief introduction of what is this matter asymmetry. We know that, thanks God, our universe is highly matter asymmetric. Otherwise, we wouldn't be here to even think about it. And this asymmetry between this imbalance between the number of baryons and antibaryons cannot just happen by statistical fluctuations or the initial conditions. So it needs some explanation, and this explanation requires physics beyond the standard model. The dynamical generation of baryon asymmetries in the universe called baryogenesis, and for that we need Sakharov conditions, which are these three conditions: the violation of the baryon number, the charge conjugation, and CP violation. And CP is basically this discrete symmetry that once it gets violated, it means that nature can distinguish between a particle and its antiparticle. And then the third condition is out of thermal equilibrium. Interestingly, all of the Sakharov conditions are actually there in the standard model. However, it's just too tiny. So in order to explain the observed value for the baryon asymmetry, we need physics beyond the standard model. And perhaps one of the popular approaches for baryogenesis is doing baryogenesis via leptogenesis, which is this beautiful idea that first we produce this imbalance between the matter and antimatter in the leptonic sector, and then with the electroweak sphalerons, we convert them to the baryonic sector. And these electroweak sphalerons are basically transitions that conserve baryon number minus lepton number, So imagine that we live in this two-dimensional plate. This L is the lepton number and B is the baryon number. This electroweak sphalurons basically make it so only that allow the transitions that are in this shade, this dashed lines, the green dashed lines. And they tend to wash out any pre-existing B plus L. So wherever we are here, we will end up with this B plus L equals 0 line. So in the end of the evolution, we will get from this initial lepton asymmetry, we will get some baryon asymmetry. And the key here in this the baryogenesis via leptogenesis is that the decay of this L is normally right-handed neutrinos, and in order for this this mechanism to work, we need sufficient CP violating phases in the neutrino sector. So that's the key in this mechanism. And then in cosmology, we have this curious cosmological coincidences among parameters, which shouldn't really be related. So one of them is eta B, which is the baryon to photon ratio today, which is roughly equal to P zeta, which is the curvature power spectrum in inflation. And then the other one is omega dark matter, which is equal 5 times omega baryons. And then if you think about standard model of particle physics, it has some conceptual issues depending on who you talk to. They may find these as like serious conceptual issues, or they might just think they are not issues at all. I personally think that's curious. And these are basically this ad hoc parity violation in the weak interaction. The fact that we only have SU2 left interactions and left-handed neutrinos, but no sign of SU2 right interactions and right-handed neutrinos. Then we have this accidental B minus L global symmetry in the standard model. We have this vacuum stability problem, and we have the strong CP problem. Okay, now after this introduction, let's get back to our question about gauge fields and inflation. Well, why gauge fields in inflation? You may ask. Well, why not? Inflation happened at the highest energy scales observable to us, and gauge fields are all over the place and the building blocks of the standard model and beyond. So what do they do in inflation? Can gauge fields actually contribute to physics of inflation? And if yes, then do they leave an observable signature so we can test them, and how much they can change the course of cosmic history? So in this talk, I will tell you that yes, they can be around, and if they were around, they will leave a robust prediction for gravitational wave background, which is their cosmological smoking gun. And if they were around, they can lead to a novel mechanism for baryogenesis and dark genesis in inflation. So in principle, they can change the cosmic history a lot. Okay, having gauge fields in inflation comes with challenges because if these gauge fields are simply given by a Yang theory, they are acting like radiation. So during inflation, they would dilute like 1 over the scale factor. And if these gauge fields, any gauge field that are active in physics of inflation should somehow break this conformal symmetry. And also dealing with gauge fields, we are not free to break them however we want, and we need to respect the gauge symmetry. It turns out that there is a common solution with both of these issues, and that's basically by adding new terms which are gauge symmetric, and they can break the conformal symmetry in the right way. The first term that we actually introduced to fix this issue, and for the obvious reason is FF tilde squared. And the reason was that FF tilde squared has the equation of a state of dark energy. In fact, its energy is exactly equal to its minus pressure. So if it was like the dominant term in the action, at first it could provide slow inflation, and eventually by injecting energy to the Yang-Mills part, which is sort of the kinetic term, inflation would end in radiation era. And this FF tilde squared is nothing but a normal Chern-Simons interaction between an axion inflaton and FF tilde if you integrate out this axion. So yeah, gauge fields who are coupled to the inflaton can survive inflation. And then it led to the third challenge, which is about the spatial isotropy and homogeneity that we observe in the very large scales. So in case that these gauge fields have a web in inflation, it cannot be a U1 gauge field, because if we have a U1 gauge field and we turn on a web, it will immediately break the spatial isotropy. However, and magically, if instead of a U1 gauge field, we have an SU2 gauge field, then it is possible to find a field configuration that's perfectly isotropic and homogeneous. And so the key is that now instead of one gauge field, we have three colors of an SU2 gauge field. And thanks to the isomorphy between SO3 and SU2, it is possible to somehow combine them and find this field configuration, which is perfectly isotropic and homogeneous. So yeah, I mean, having SU2 gauge fields or any non-abelian gauge field sitting in this SU2 subsector, you can actually solve all of these issues. Are there any questions so far? Okay, no. In other words, let me show you some action. So the first model of SU2 gauge fields in inflation was gaugeflation, which is basically in the Einstein gravity, we have a normal Yang-Mills term plus the self-interaction for the gauge field FF tilde squared, which acts like a sort of like a potential term. And then gaugeflation is basically an effective field theory coming out of a larger model called Cosmological, which is axion-inflation, like a natural inflation, when you extend that with some SU2 gauge fields that are coupled with the inflaton with a Chern-Simons interaction. So what is interesting here is that it can somehow fix the issue of natural inflation. Natural inflation has this issue that the cosine potential is not flat enough, and in fact, it's very steep. So in order to have enough number of e-folds, one needs super Planckian F value, and F is our cutoff, so it's problematic. What is interesting about Cosmological is that although the potential is still not flat, but this interaction with the gauge field provide a friction term. So although the potential is steep, but when the axion is going to move in the potential, it faces a lot of friction, and this friction slows down the evolution, and we will have enough number of e-folds, and we will have slower inflation. So far, so good, but unfortunately, both of gaugeflation and Cosmological are now ruled out by the data, and also both of them suffers from some theoretical issue. So if I want to show you in the Cosmological case, the problem is that in order to provide this large amount of friction, to provide enough number of e-folds, this lambda should be very large. And it's really hard to explain that from the theoretical point of view. And for the same reason, both of these models produce lots of gravitational waves, and that's the reason that they ruled out by the data. But inspired by these two original models, several different models with SU2 gauge field have been proposed and studied. Here we have an incomplete list of different realizations of the SU2 axion-inflation. But why so much attention? The reason is that this class of models has a very rich phenomenology. And so it leads to a new mechanism for generation of primordial gravitational waves, and that actually turned this topic to a hot topic. And at the same time, all of the Sakharov conditions are satisfied in inflation. Therefore, it leads to a new mechanism for it. It provides a perfect setting for baryogenesis in inflation. And also because we have an active gauge field in physics of inflation, it leads to particle production by Schwinger effect and chiral anomaly. Okay, then among all this different realization that I showed you, I choose this minimal scenario of SU2 axion-inflation, which is basically, I replaced the cosine potential in the cosmological model with a potential which is not cosine, but it's flat enough by itself. So if we assume that, then basically lambda can be as small as we want, and it can solve the problem with the data and also the theoretical issue. Are there any questions so far? Okay, no. So how to connect this gauge field with the standard model? Let us extend the standard model gauge symmetry by an SU2 right and couple it to the axion-inflation. So here I consider the left-right symmetric model plus an axion. And now I assume that this SU2 gauge field, which is coupled with the axion, is the SU2 right. And of course, it can be the SU2 left as well, but I will tell you that this effect will get washed out. So I only focus on the SU2 right interaction with the axion for now. The left-right symmetric model particle physics is proposed by Patty and Salam to actually solve this ad hoc parity violation in the weak interaction, and the fact that we have SU2 left and left-handed neutrinos, but no SU2 right and right-handed neutrinos. And then because of its interesting features, it received a lot of attention and extensively studied in the 80s. So if we want to add an SU2 right in the standard model gauge group, then something interesting happens. And that's that we need to also upgrade the U1 hypercharge with the U1 B minus L. So the baryon number minus lepton number. And so now in the gauge sector, we have the strong, the gluons, we have this gamma for the U1 B minus L, we have the standard model SU2 left, and this SU2 right gauge fields. And also it naturally extends the standard model fermionic sector with 3 right-handed neutrinos. Now when this extra symmetry is spontaneously broken, we will get from this SU2 left times SU2 right times U1 B minus L, we will get the standard model electroweak sector. And at that point, so that's in order to actually provide our setup with this extra spontaneous symmetry breaking, we need an extended Higgs sector, which is now apart from the, like in the standard model SU2 left doublet, we have to extend it to an SU2 left times SU2 right bidoublet, and we need to add two SU2 triplets, one for SU2 right, the other for the SU2 left. And then at some point when the SU2 right triplet gets its wave, then it will break this extended gauge symmetry to the standard model electroweak, and it gives Majorana masses to the right-handed neutrinos and to W right plus and minus and Z right. So interestingly, this minimal left-right symmetric scenario can actually solve all of these issues, this conceptual issues, if you think they are issues, of the standard model, because now we have the mirror version of the SU2 left and left-handed neutrinos. This accidental B minus L groove asymmetry in the standard model is now gauged, so we can explain why we have it in the standard model. Because of its extended Higgs sector, it can explain the vacuum instability problem, and because now it added parity in the setup, it can also solve the strong CP problem without an axion. In this inflationary scenario, I embedded the axion-inflation in the left-right symmetric model. And as the minimal realization, I coupled that with W right. You can also add it with W left, but then I will tell you what will happen. So what's happening is that now, apart from the weak scale in cosmology, we have this extra like new fundamental scale, which I call feeble scale, during which the extended gauge symmetry is broken to the standard model gauge symmetry. That feeble scale can happen either before or after inflation. In this type, I focus on type 1 scenarios in which this symmetry breaking is happening shortly after inflation. And because of the interaction between the axion and the particle physics, parity is spontaneously broken in physics of inflation, and also CP is broken. So let's get to the gauge field production by the axion. In this setup, the standard model gauge fields are diluted by the exponential expansion in inflation. Therefore, they are not important. But this SU2 right, which is directly coupled to the axion-inflation, and the gauge field keep pumping energy to it. So it is active in inflation and get generated. This is the field equation of this gauge field. I decompose it in terms of its just two helicity states, plus and minus. And as you see, the effective frequency square of this guy depends on its polarization state. This parameter psi is related to the time derivative of the axion, like this. So this psi is basically 2 lambda over f times phi dot over h. So phi dot over h is roughly square root of epsilon, the slow roll parameter. So in inflation, if the axion field has a positive bev, we will have this red slow roll trajectory, and psi is positive, this parameter. However, if the web of the axion is negative, then we are living in the parity conjugated version of the slow roll, which I showed by blue, and here psi would be negative. If psi is positive, then we are actually producing more of the plus polarization of the field. So what is happening is that here in this white box on the right-hand side, we have B plus and B minus in terms of the physical momentum. As you see deep inside the horizon, they are actually more or less like a quantum fluctuation. But when we are getting close to the point of horizon crossing, then this term will be larger. And that's the point that the plus helicity state experienced this short phase of tachyonic instability, and it grows However, the minus helicity state is just decaying, but then eventually both of them will decay, the plus one much slower. As a result of this short phase of tachyonic instability, we will have particle production around the horizon, which is related to this parameter psi as this, and is also related to the scale of inflation. Are there any questions so far? Can you hear me? Okay. So what is interesting is that now this gauge field is sourcing gravitational waves. So comparing to standard scenarios in which the right-hand side is 0, here we have a non-zero source for gravitational waves. And so now the total form of the solution for gravitational waves would be the homogeneous solution, which is basically the vacuum one, which is unpolarized and nearly Gaussian. And the second part, which I showed in pink, and that's the one that's sourced by the gauge field. So it's sort of the carbon copy of its source, and it's polarized and non-Gaussian. And so it actually, the form of non-Gaussianity is in the equilateral shape, and it can be probed by future CMB missions like LIGHTBIRD and CMBS-4. But it's not all. In fact, these gravitational waves are blue tilted because you see that they are sourced by the gauge field, and the gauge field is the generation of the gauge field is related to this parameter psi. Because psi is related to the time derivative of the axion and is increasing with time. Therefore, we're actually producing more sourced gravitational waves as we get to the end of inflation. And that's why these gravitational waves are blue tilted. Therefore, even if it's if the signature, that the source part of the gauge field is not strong enough to be probed by CMB missions, still there is hope for that to be probed by future laser interferometers. And the key, the trick is that it predicts a chiral gravitational waves with the same chirality all over the sky. Therefore, you won't miss it with astrophysical sources. Also, another interesting thing is that because parity is spontaneously violated in physics of inflation, we have non-zero TB and EB in this setup. So then one question is that how to distinguish that with the cosmic birefringence. So cosmic birefringence is this interaction when you modify the Maxwell equations and you couple the axion with the photon, then what's happening is that from the surface of CMB till today, it will rotate the electric and magnetic field, and it will sort of give some signature at higher L's. In this scenario, this SU2 axion-inflation, the signature is actually because of the interaction with the graviton, like the gauge field and the graviton are coupled, and that will modify it in comparing to the standard scenarios from the end of inflation till the surface of CMB. So this signature is actually at lower L's. That's why it's distinguishable from the cosmic birefringence. And it has the same structure as the gravitational Chern-Simons interaction. And that's basically when you modify gravity with this interaction between the axion and R tilde, then it also produces chiral gravitational waves, and the form of TB and EB that it will produce is the same. However, it's easier for this SU2 axion-inflation to produce this chiral gravitational waves, and it's more efficient. Okay, so let us go to fermion production. by the SU2 gauge field. So all the left-handed fermions are diluted by the inflation because all the fermions are massless and they are coupled to a gauge field which is not active in inflation, so they have conformal symmetry and they are diluting. But the right-handed fermions are generated by SU2 right gauge field. And the key ingredient is the chiral anomaly of the SU2 right in inflation that produce exactly the same amount of baryons and leptons in inflation. So the final baryon number and lepton number are given like this, and it's related to the scale of inflation, and this parameter alpha inflation, which is related to parameter psi, which was the factor that actually specify the amount of gauge field that we are producing. But remember that, so now in inflation, we have equal amount of baryons and leptons. All these baryons are in the standard model, but in this leptons, part of that are the standard model leptons, and part of that are the right-handed neutrinos. So this is a summary of this mechanism that was happening in inflation. The chiral anomaly of W right produce B equal L, an equal amount of baryons and leptons, but it is a non-zero B minus L in the standard model sector. Then shortly after inflation, this new gauge symmetry is broken to the standard model 1. So the SU2 right times U1 B minus L is spontaneously broken to U1 hypercharge. And then shortly after that, the W right is decoupled at TW right, which is freeze-out temperature. And so here I assume that among these 3 right-handed neutrinos, only 2 of them are very massive and contributing in the seesaw mechanism. But the lightest one has feeble Yukawa interactions, and it's therefore stable enough to be a dark matter candidate. So at this point, this N1, which is the lightest right-handed neutrino, will get decoupled. And then from reheating till the end of electroweak scale, we have lots of Swallow-Run process. We have the Swallow-Run processes, and we have the Yukawa interactions and the spectator effects that reshuffle as this pre-existing baryon number, lepton minus lepton N1. And also we have N2 and N3, which are decaying to the standard model. So in the end, we will have this final values of baryons, lepton standard model, and N1. But something, let me mention, so something is very important about this mechanism. In order for that to work, we need that the reheat temperature is lower than the decoupling temperature of W right. And if that's the case, then it immediately guaranteed that the reheat temperature is lower than the mass of W right. And so this blue shaded area is where the SU2 right Swallow-Runs are in thermal equilibrium at some period. The pink shaded area is where we are interested in. And so it means that if this condition is satisfied, then the right-handed, the SU2 right Swallow-Runs are never in thermal equilibrium. And that's very important because if they were in thermal equilibrium, I didn't generate any B minus L total. And if they were in thermal equilibrium, they would basically wash out anything. But from reheating to electroweak scale, only the SU2 left Swallow-Runs are in thermal equilibrium to reshuffle the leptons and baryons. In case that I also couple the inflaton with the SU2 left gauge field, everything would be basically the same, but so I would have a 0 B minus L in this anomaly sector, and they are in thermal equilibrium. So that part wouldn't contribute to any baryon number and lepton number standard model, because it would totally washed out by the SU2 left spallerings. So this mechanism actually provides it provides a new framework in which a pure quantum effect in inflation, chiral anomaly, provide a common origin for baryogenesis and cold dark matter. As for the mass of this cold dark matter, which is basically the lightest right-handed neutrino, its mass should be around 1 GeV, and this is the final form of the baryon number over photon number in terms of H, scale of inflation, alpha inflation, which is basically the fermion production by the gauge field, and this delta reheat, which somehow a phenomenological parameter by which I parameterize the efficiency of the reheating. Okay, and so what is curious and sort of interesting is that the setup prefers this left-right symmetry breaking scale, like the scale that SU2 right times U1 B minus L breaks to U1 hypercharge, to be, it prefers mass scales which are higher than 10 to 10 GeV. And that's curious and interesting, because that's the scale that's suggested by the non-SUSY SO10 GOT models with intermediate left-right symmetry scale. So that's something curious. And another interesting thing is that it also demands that the symmetry breaking happens shortly after the end of inflation. So somehow it hints interactions between the axion, between the inflaton and this delta right, which is the SU2 right triplet Higgs. So that's another interesting thing that right now I don't have any explanation, but just happened to be the case. So as a compelling consequence, the setup can explain, can provide a particle physics for inflation, can explain the origin of the matter asymmetry, the origin of the neutrino mass, and the particle nature of dark matter. And because, so basically it provides a common origin for the dark matter and baryogenesis, and it deeply related that with inflation, it can also naturally explain these cosmological coincidences. And yes, if I want to as for my conclusion, let me just compare that with the minimal setup that that can explain all those issues. So this minimal setup is based on inflation particle physics, just having one scalar field, like a scalar singular beyond the standard model as the inflaton. In that case, then we will have unpolarized Gaussian primordial gravitational waves. And if the source of baryon asymmetry is the baryogenesis via leptogenesis, then it requires CP violating phases in the neutrino sector. And normally, it also demands fine-tuned relations between the masses of the heaviest right-handed neutrinos. And as for the dark matter, one natural candidate can be a stride neutrino dark matter, but it generally, I mean, most of the time, its mass is around 10 keV, and its radiative decay will provide X-ray radiation in the highly dense dark matter areas in galaxies. This SU2 right axion-inflation scenario that we discussed here provides actually propose an inflation particle physics based on an axiom which is added to the left-right symmetric model, and the axion is coupled to the SU2 right gauge field. It can also be coupled to SU2 left, like SU2 right times SU2 left. Because the gauge field is active in physics of inflation, it provides a robust observable signature, and that leads to chiral non-Gaussian gravitational waves, which will be probed by future CMB missions and laser interferometers. It provides a new mechanism for baryogenesis and right-handed neutrino production based on because now CP is broken in physics of inflation, and also the lightest right-handed neutrino can be the dark matter candidate, and its mass is around 1 GeV, which its radiative decay can produce gamma rays. It also has a new fundamental scale comparing to this minimal setup, because now we have this extended gauge symmetry. It provides a simultaneous baryon and dark matter production mechanism originated from inflation. Therefore, it can explain naturally these coincidences among cosmological parameters. Okay, thank you very much. Are there any questions?
Yeah, let me ask a question just to make sure. Oh, sorry.
That's where we take that.
Yeah, you will go for it.
Oh, sorry. I thought Jojesh was asking something.
Yeah,
I just want to make sure that I understand. I mean, I think the inflation here is just driven by an ordinary axion-inflation model, right? So
Yes.
it's not that you're doing trapped inflation or particle production or quote unquote warm inflation here. The particles are produced on top of the inflation, which is dominantly driven by the axion potential, right?
That's a very good question. That's a very good point. The thing is that for warm inflation, so we're actually pumping energy to the gauge field sector. So we are actually pumping energy to radiation. The thing is that in this work, I didn't consider the thermal effects, but they can be there. I just didn't consider them.
Well, yeah, I just mean, you know, as you explained, you had a previous incarnation where you were using particle production to slow down the inflaton, as does work for scalar fields in other contexts, but here it gave too strong a gravitational wave signature. And then instead you pivoted to use just an ordinary slow roll inflation model, on top of which you have some additional effects. So in that, I just wanted to verify that my understanding that in that sense, it doesn't require, you know, the particles that are produced are some kind of perturbation on that overall inflation model, which is obtained via the usual slow roll conditions. Is that correct?
Yes, exactly. So
Okay.
I didn't mention that. Thank you for pointing that out. The thing is that, so we started thinking about this SU2 gauge field in inflation, and for many years we assumed that there is a web of this gauge field. In this last work, I didn't assume that it has a web. I just turned it on as a quantum fluctuation that get generated by the axion. And the reason is that so now I need a rather large gauge coupling. The G right gauge coupling is around the G left gauge coupling. And in that case, if I turn on a web, then I need to actually recalculate everything that we did before, because that previous calculations are based on much smaller gauge fields, gauge couplings. Here, I didn't want to do that, because that was the first step. I just assume anything, and like I just consider the most minimal thing. Yeah. Oh, Professor Patti, what an honor! Thank you very much for coming.
Oh, I don't know. Can you hear me? I mean, I don't know
Yes.
what I should. Okay. I have two questions. I enjoyed your talk. The first is practical. You said that your two right-handed neutrinos N2 and N3 are heavy, whereas the third one is of order 1 GeV. How heavy is the N2 and N3?
Very good question. Sorry, Eva. Let us discuss after Professor Patti. I just got so excited, and yeah, sorry. Yes, the thing is that I assume the hierarchical mass spectrum for right-handed neutrinos. I assume that the heaviest one is around 10 to 12 GeV, and the second one 10 to 9 GeV. But I just something, because I want to calculate the flavor effects. That's why I assume that, but it's not like a necessary condition. However, since this mechanism requires a heavy MW right, I assume that if the Yukawa couplings of N3 are around 1, then I would expect that the heaviest one would be around, would be, of course, it cannot be less than 10 to 9 GeV. But in that paper, in calculating the flavor effects, I assume that the heaviest one is around 10 to 12 GeV, and the second one is around 10 to 9 GeV. But if you assume other things, it wouldn't change that much. Just something that I chose.
Okay. No, well, before I ask the second question, the reason I asked this question about how heavy, because your N1 is so light, is that if one tries to consider the within some SO10 type or SU2 left, SU2 right, SU4 color type symmetry structures, the mass spectrum of quarks and leptons, and try to have a predictive pattern for both quarks as well as neutrinos, usually one finds that, and I'm saying more in the supersymmetry context, one finds that these masses, N1 is not that light, and N2 and N3, at least N3 is heavier, like more like 10 to the 14 GeV, and that correlates with the atmospheric oscillation mass scale numerically, very beautifully within the SU4 color symmetry. So if one takes the symmetry in more seriously, then there are constraints. If you try to fit different masses, not just fit, but predict also, like the atmospheric mass scale. So that was a comment. Do you see what I'm saying?
Yes, yes.
This work has been done. This work has been done, for example, in the work with Wilczek and Babu and so on. But I understand the spirit of your work. All I was saying is that it may not be as free as one would like, and that remains a challenge in that case. The mass scales that you are needing.
So how heavy would be the lightest one? Is how heavier?
Well, no, of course. I mean, yeah. I guess maybe I should just ask the second question. Have you at least considered supersymmetrizing the model?
Not yet. It's one of it's definitely my to-do list and my blackboard, but not yet.
But I mean, basic idea will remain. The only thing will be the nature of the dark matter. That dark matter could come from the supersymmetry sector. So that was my comment. And then,
Excellent
of course,
point.
the unification goes well with supersymmetry. So, but thank you very much. I mean, enjoyed your talk.
It was an honor to have you here. You really made my day. Thank you very much. Sorry, Eva. I think I just jumped. Did I answer your question, Eva?
You did, yes.
Yeah, I'm
Mine was a
asking
comment.
Eva. Sorry.
I think I got my answer. I was right that it's just ordinary inflation.
Yes.
Yes. Okay. Got it. Thank you.
Thank you.
I think Michael has a question. Is that right? Whoever has a question can
There we
just
go.
unmute
Yes.
themselves and ask a question.
Great. I have a couple questions.
Yes.
The First of all, what is the mechanism for getting that one neutrino flavor, very light but at a non-zero mass, where the others are up at the scale that you would require for the seesaw?
That's a very good question. The thing is that, so typically people are assuming something like extra discrete symmetries that can explain that like huge
Then this has to be-
hierarchy.
Then this has to be weakly broken in some way, the symmetry?
Yes, because eventually it got, because if that discrete symmetry is there, then basically the lightest one is totally massless. Unfortunately, I don't have a good answer for this setup, but I know that, for example, in minimal neutrino standard model, when they want to explain that, they actually had this argument, or other particle physics. I don't know about this one. Maybe Professor Patti had some answer for that.
Well, I kind of commented on that, what Michael is asking, that if you do everything connected in a way that you try to correlate with quarks and leptons and try to sort of have a predictive structure, then I don't think one can get this big hierarchy between the three. The heavier one tends to be a little heavier, like 10 to the power 14 GeV, the heaviest one. Then about 10 to the power 12. And then the next one can be 10 to the power 7, as light as 10 to the power 7. But between 10 to the power 7 to 10 to the power 9. And that goes well with a predictive system.
Yeah, but maybe the supersymmetry is too restrictive.
Pardon me?
Maybe supersymmetry is too restrictive here.
No, I was simply saying this part of the, yes, the structure is supersymmetric, but that didn't play a role in this discussion of the masses, and it played a role in the scale of the heaviest one, because I took the unification scale to be 2 10 to the power 16 GeV. Then things become predictive on the atmospheric mass scale, which comes via seesaw, and the SU4 color Dirac mass related to the top mass, and that for the third family. And that kind of sets the pattern, and you can then predict the masses of the three neutrinos, the right-handed, well, they come from the right-handed neutrinos. Then it doesn't become feasible, as far as I see, to have the N1 being that light with the heavier ones being much heavier. I guess that was your question, and I think to the extent I have played with it and with others, it doesn't seem to be that feasible. But again, I think the attitude here, as I sense from the talk, has very beautiful structure, is to leave this a little bit loose, this mass scales, but maybe it can be modified. This may need some more looking into.
Yeah, that's.
Okay, and then the second question. In this model, the dark matter direct detection cross-section is essentially 0 because it comes from some operator with the mass scale 10 to the 10 GeV.
Yeah, as far as I see, yes. So, so yeah, it wouldn't. I'm not very optimistic that it has any like particle collider signature. But the signature is in the gravitational wave background.
Okay. Well, I was asking about the direct detection signature, but that also seems to be extremely small, unless I missed something.
Yes.
Okay, and then finally, the connection between the right-handed and left-handed sectors comes from the neutrino, the decay of the heavy right-handed neutrinos. So could you just explain, just very briefly, how that leads to an asymmetry in the left-handed neutrinos that you're going to then use in leptogenesis?
Yes, let's see.
I think you explained this, but I missed it somehow.
So if this, so maybe this slide or the other one?
Maybe this slide, yes.
Okay, perfect.
So the baryons stay the same, and the leptons get shifted in okay.
Yeah,
You,
in the
you should go ahead.
okay. So yeah, the thing is that here we produce equal amount of baryons and leptons, but B minus L in the standard model is not zero because, yeah, here we are. So the shaded, yeah, it's, sorry, it's a stupid way to explain it. Yeah, maybe it's better here. Sorry. Yeah. So we are producing equal amount of baryons and leptons, but part of this lepton is not in the standard model, but the right-handed neutrinos. So the baryon minus lepton number in the standard model sector is not zero. And then what's happening is that I have this N1, which is decoupled after the freeze out of W right. Here, part of the leptons now is this N2, N3. They will decay at the right temperature.
N2 and N3 always decay to N1 plus some other products, right?
Yes. The thing is that that's a very good point.
And then the other products have to have their own asymmetry, which turns up to be the baryon asymmetry that we see.
The thing, excellent point. The thing is that this N2 and N3, when they decay, they will partially wash out this pre-existing asymmetry in the, so for example, if this N2 and N3 are producing like in the standard model flavor space, if they are producing leptons in this direction, they will wash out the pre-existing one at this direction as well. I assumed in this work, I assumed that the amount of CP violating, the CP violating phases in the neutrino sector are not large enough to compete with the pre-existing amount of B minus L. So I'm producing something in this direction, and it washed out partially. Let's see, maybe I have some slide better.
I'm just trying to understand how the asymmetry doesn't end up entirely in the dark matter rather than in the observable sector, given that N1 is a product in every decay.
Right. The thing is that, so I'm washing out part of that, but it's just, so this directions, I simply assume that the CP violating decay of N2 and N3 are not large enough. So so the secondary generation of B minus L by this decay is negligible compared to the pre-existing one. But then it will partially wash out this B minus L in its preferred direction. The thing is that one can show that this washout effect is cannot wash all of the B minus L. It can just wash out part of that. And the reason is that in order for the N2 and N3 decay to totally wash out this pre-existing B minus L, it requires extremely fine-tuning between this direction, the decay direction of N2 and N3 with the direction of pre-existing lepton asymmetry, which is flavor blind and happen in inflation, and that's almost impossible. So it cannot wash out that effect completely. It can. So in most of the parameter space, after the decay of N2 and N3, we will get a B minus L, which is roughly 1/3 of the pre-existing B minus L. And what else? And then I also assume that this the secondary generation of N1 by the decay of N2 and N3 are negligible. You can assume otherwise. I just want to study the most minimal scenario. And then what else? Oh, something. If I answer your question about that, then I can. I have to also show you this. The thing is that so after so now that the reheat temperature is lower than the freeze out temperature of W right, of course this right-handed neutrinos wouldn't get any like freeze out generation, but still the scattering with W right can generate some right-handed neutrinos after inflation by the freeze-in mechanism, and so that you can assume that this generation is negligible, or you can consider that. So here in this plot, the solid lines are just when for a given MW right, you assume that the reheat temperature is lower than T W right, and then the shaded the dashed version of every line associated with the same mass and setup once this freeze in production of N1 is negligible comparing to its pre-existing one, and that's when you get this mass. Did I answer your question?
I think I got it. No, I think that's good. Thank you very much.
Thank you very much for joining and for yeah, it's an honor.
I think Glenis is asking you to return to the full screen because I think the slide became too small.
Oh, okay.
Does anybody else have questions? No. I had a question actually related, I think, to what Eva was asking. So you are not using this friction mechanism of warm inflation, but did I understand it correctly that all the baryons and all the dark matter gets produced during inflation and does not get diluted? I mean, it gets constantly repopulated. So it is not some standard inflation where, during inflation, you only produce, say, curvature perturbations, and then all matter and dark matter just gets produced after reheating, right? So it's a bit different in this sense, right?
Yes.
So the question that I had is, what happens to perturbations in a sense that, what is the spectrum of perturbations that these baryons and dark matter that were produced during inflation that they carry? Is this approximately scale invariant, or is it different? Because you had this extra time derivative, right? This was bringing up some tilts to that spectrum.
So the thing is that, as I said, there are like two versions of SU2 like axion-inflation models. So previously we assumed that this SU2 has a wave, and that actually, because of that wave, it contributes to linear scalar and tensor perturbations at the linear order. and that has to be considered. In this setup, I assume that these gauge fields are only get generated as like a quantum fluctuation sourced by the axion.
But
So
fermions get produced from that gauge field. Did I understand it correctly?
Yes, yes, and these fermions are the generating mechanism is similar to the gravitational wave one. So although these gauge fields are actually eventually at super horizon scales are actually diluting, but because of their generation around the horizon crossing, these fermions and gravitational waves, which are sourced by the gauge fields, are given by, so you have to solve the green function integral of the gauge field. And that's, so although the gauge field itself decays, but these fields memorize their scattering with these gauge fields. So that's why
there is a finite density of baryons and dark matter
baryons,
throughout the inflation. Is that correct?
Yes.
That survives
Yes.
until today.
Yes.
And I guess the question I'm trying to ask is it obvious that there are no problems with isocurvature perturbations coming from this, right? Because it is something what we would call an isocurvature perturbation, right? It's the second fluid that existed. I mean, that's independent of the density, usual zeta perturbations, right? So what? How large is that contribution?
That's a very good question. The thing is that so this particle production, the fermions and gravitational waves, they are related to this parameter psi, which is increasing with time. So at the scale of inflation, this psi, if it's around, let's say, 3 or less than 3, then the back reaction and the effect of this particle production on the cosmic perturbation at CMB scale would be negligible. But then after like CMB scale, it get increased because this parameter is increasing with time. So the thing is that what we see on CMB is smaller than so in this mechanism, so most of the fermions are actually generating after the CMB scale.
Fermions are generated after the CMB scale.
No, they keep getting generated, but the thing is that like the gravitational wave one that gets enhanced by like
sorry, can we not discuss gravitational waves for a second? Can we just discuss the scalar density perturbations that includes baryons and dark matter? Okay, never mind baryons, just we can just discuss dark matter.
The thing is that so it this gauge field actually source scalar perturbations at second order, and also the fermions at second order. The thing is that the gauge field production is more efficient. So this is the one that that actually make most of the contribution. I have actually a plot. Maybe that's a better answer to the question. Oops. Shoot. Sorry. Is the size okay, or if I want to get back?
I think if you could make it bigger, no? Just go on the right, this thing, make it bigger.
Okay, great. This one is when the wave of the gauge field is on, but sort of the same story is true when the wave of the gauge field doesn't have a wave. I just want you to have a feeling about the strength of these particle productions. You see the largest contribution is coming from the gauge field itself. Then we will have the contribution of the fermion production, And then the smallest one is for the scalar production, all sourced by the gauge field. So, if we are talking about the modification of the scalar perturbations in this mechanism, then the largest contribution is actually the second order contribution of gauge fields. And then the fermion production is actually much smaller. So although it can explain the matter asymmetry we observed today, but its effect on CMB scales is subleading comparing to the gauge field itself. Did I answer your question?
I think so, yeah. I think that's kind of what I was asking. And you say the gauge field's contribution also does not work as a dangerous Isaac curvature perturbation.
Yes, even with the VEV, if psi parameter is smaller than some amount, then that's the case. But in this case, in this scenario, I don't have a VEV, so yeah, it's much better. But I would say, if I want to be conservative, I would say that the scale of at the scale of inflation, psi should be less than 3. So we won't like generate any dangerous like modifications.
I see. Okay, thank you. Does anybody else have questions? Okay, that's if no, then let's say Azadeh for a very nice talk.
Thank you very much for the invitation. Thank you for joining and the wonderful questions.
Okay, goodbye everybody. Thank you.